Good evening, everybody. Welcome to Chem 170 with your host, me, Dr. White. How you doing? Tonight, I'm going to be going through the review for test 4. Let me just remind you that this Thursday, I'll be giving test number 4 like I gave the others Thursday morning or maybe even Wednesday late night. I'll send out the password for the PDF file for test 4. You have until Friday, 11:59 to finish it and upload your answers. Now, test number 4 will cover polymers, lipids, also known as fats and oils, and carbohydrates. It has 9 pages, 20 problems. Some of the problems are multiple part, and here's the point breakdown. 54 points general knowledge, 15 points nomenclature, 36 points reactions. So there's five bonus points, but 54 points general knowledge. What's going on? Well, if I ask you, is your left hand chiral or achiral? Well, that's not nomenclature. That's not reactions. So it's general knowledge. If I ask you to circle the chiral carbons in a molecule or draw the enantiomer of a molecule, that's not nomenclature, that's not reactions, so it's general knowledge, and that's why it's so many points. Now, one thing I do want to point out, if we go to the content area of D2L, and in the lecture section, if you scroll all the way to the bottom, because D2L is ancient software, see where it says load more. Again, scroll all the way to the bottom of the lecture folder, and you'll see a button that says load more. And if you click on that, there's more files. And if you scroll down, you'll see the review for test 4, both as a Word document and a PDF file. And that's the slide I'll be working on, or slides, or the file. Everything you see on the screen in this video, or if you're watching me live right now, will be from those 2 files. All right, let's go through test 4 review. As with my other reviews, the information you should know for test number 4 are in the review. All right, let's start out with what's a polymer. And you should know a polymer is a macromolecule. That means a big molecule. I mean, big molecule made up of repeating units called monomers. Now, you should know there are 2 ways of distinguishing polymers, types of polymers. One is by a chemical property, the other is a physical property. And you should know that under a chemical property, we have an addition polymer. And you should know what is an addition polymer. That's a polymer with only one type of monomer. And you should know examples of that are rubber car tires or bicycle tires. And another one would be saran wrap, kitchen plastic wrap. Now, the other type of chemical property or type of polymer by chemical property is a condensation polymer. And a condensation polymer is a polymer with 2 or more types of monomers. Think of it this way. If you had a freight train addition polymer, all the cars would be identical. In a condensation polymer, you'd have alternating types of cars in the freight train, or tank wagons and boxcars. Dr. White's a train addict. I like trains and model trains. All right, the other type of way of type of polymer, identifying them, is by physical property. And there are 2 types. A thermoplastic polymer is a polymer once formed, it can be reheated and reshaped. An example would be my plastic water bottle. And by the way, this is also a condensation polymer. I forgot to mention that. And saran wrap is also a thermoplastic. There's no correlation between addition and thermoplastic or condensation. Those are just separate, and you can have one be one here and paired with another different one like you see with plastic bottles and saran wrap. Now, the other type of thermal property is thermoset polymers. And those once formed, it cannot be reheated or reshaped. Example of that is rubber tires like car tires, or urethane foam like in your pillows or your furniture or your car seat. All right, let's move on to fats and oils. All right, lipid. That's a molecule made from living things, from plant and living things that are soluble in nonpolar solvents and not in water. And later on, I'll be talking about what's the nonpolar and polar solvents. All right, now you should know a saponifiable lipid, also known as fats and oils, yields carboxylate anion of fatty acids in the reaction with base and water. You should know, hint, that a saponifiable, let me get real subtle. And I should have done it up here too, but I'll do it now. These are things you should know. I've never asked what's a lipid on a test, but you should know saponifiable lipids are fats and oils, and they yield carboxylate anions of fatty acids in the reaction of base and water. And you should know non-saponifiable lipids, also known as steroids, do not react with base and water. All right. Since I'm being subtle tonight, you should know a fat is a solid or semi-solid triglyceride at room temperature, and an oil is a liquid triglyceride at room temperature. Now, all fats and oils are this triester, triglyceride. And this is an area I worked in for a number of years. And we write it instead of like this, fats and oils chemists write it differently like this, where this is our group here, and here are the different R groups attached to the carbonyl. Now, there are three esters. Ester number 1, ester number 2, ester number 3. Good news. The general reactions that you learn for test 3 with esters, fats and oils undergo the same thing. So if we have acid hydrolysis of fat or oil, you have the three esters, acid and water. If I write my ester this way, you still get the alcohol plus the carboxylic acid you would have used to make that ester. This case, first ester, this alcohol plus this carboxylic acid, second ester, this alcohol, this carboxylic acid, third ester, this alcohol, and this molecule with the three hydroxyl groups is called glycerin, which I'll never ask. But since I worked at a company that made about 100 million pounds a year of glycerin, 100 million pounds a year, roughly, maybe even more, of the carboxylic acids from fats and oils. It's nice to talk about it. And you get these three different carboxylic acids depending on what our prime and our double prime are. For base hydrolysis, base and ester, you get back the alcohol plus the carboxylate anion of the carboxylic acid you would have used to make that ester. You have three esters, you get glycerin, and each ester gives the different carboxylate anion. Now, one thing we didn't talk about during esters for test 3 is steam hydrolysis of fat or oil. And you can catalyze the reaction by A, using a catalyst, or B, most reactions, not all, increasing the reaction temperature. And steam is very, very hot water. So the reaction products for steam hydrolysis of fat or oil are the same as acid hydrolysis. You get back the alcohol plus the carboxylic acid you would have used to make that ester. Here we have our three esters, we get glycerin again, and we get these three carboxylic acids. Now, the carboxylic acids you get from this type of hydrolysis or acid hydrolysis, since they come from fats and oils, organic chemists are lazy. Instead of calling them fatty carboxylic acids, we just call them fatty acids. And there are two fatty acids I would like you to know the structure of. Whoops, wrong color. And the first one is stearic acid, which is a saturated fatty acid, meaning only carbon-carbon single bonds, and has 18 carbons. Notice instead of writing CH2 16 times, I used a parenthesis subscript 16. That's a shorthand. The other one is oleic acid. And oleic acid also has 18 carbons, but it has a double bond, and this is at carbon number 9, C9. 7 plus 1 is 8. That makes that number 9. And that's oleic acid, and that double bond can be cis or trans. Now, I'm not going to write hint again, but you should know a saturated fat only has carbon-carbon single bonds. A saturated fat only has carbon-carbon single bonds. Unsaturated fat has at least one carbon-carbon double bond. Unsaturated fat has at least one carbon-carbon double bond. Mother Nature never did triple bonds in anything she ever made. Organic chemists did, but not Mother Nature. Now, because I worked in this industry for a number of years, I was both lab manager for research and development for Unichem Chemicals for all of North America. Plus, I ran their QC lab for a major chemical plant on the south side of Chicago. I have taught you the following. You should know tallow is beef fat, yellow grease, a type of pig's fat, white grease, a type of pig's fat. And the chemical company I work for, each week we would buy, depending on the market needs, 2 to 3 million pounds of tallow, yellow grease, and white grease. We try and get yellow grease and white grease because it was a couple pennies cheaper. And if you're buying 100 million pounds and you can save 2 cents a pound, that's a lot of money. All right, now to give you a realistic feel of what's going on, I came up with an idea. Let's call both tallow represent tallow, yellow grease, and white grease by this structure. Our sabot is a sterile group, arsobacestero, arsaboaleal. And when you hydrolyze it, you'd get stearic acid. This would give you oleic. This would give you, that's a good thing. So you should be able to do, well, if I take tallow and sodium hydroxide and water, you get three products. What three products? Well, this is base hydrolysis of an ester. You get both the alcohol plus the carboxylate anion, the carboxylic acid used to make that ester. Well, tallow is really, and so is white grease and yellow grease, and we used to interchange them and get approximately the same amount of the different fatty acids, mainly stearic and oleic. The first ester gives you this alcohol plus sodium stearate. Second ester gives you this alcohol plus sodium oleate. And the third ester gives you this alcohol, so you get glycerin. And you once again get sodium stearate. You don't have to put the two here. But those would be the three different products. When you get two of something, it's not as different product. You should know how to take tallow, white grease, and yellow grease, react it with also, instead of NaOH and water, acid and water, and with steam. Now, in this area, an important thing you should know. I better be subtle about this. You should know how soap works. Leaving my class, I expect all of you to know how soap works. It's an important part of our life. First of all, you should know the structure of soap. All soaps have a nonpolar tail and a polar head. And then, and I don't have it down here, I better put it down. But I mentioned it. Their designation, polar or nonpolar, different substances. Water is polar, alcohols and salts are polar. Then they're nonpolar things. And for this thing, dirt and grease, oops, D fell off, are nonpolar. And the key to this, and if I were in a classroom, I'd write it super big. The key to the puzzle, how does soap work, is like dissolve like. That means polar things are soluble in polar things, nonpolar things are soluble in nonpolar things. And if you mix two together, they're not soluble. Just like an oil vinaigrette dressing separates. And that's where soap comes in with its nonpolar tail and polar head. Water is polar. So you're not going to get dirt off your hands or grease with water. No. But when you use soap, and if this was a little highly magnified piece of dirt, you should know the soap molecules, the nonpolar tail is attracted to nonpolar dirt, and the polar heads of soap stay way out on the outside. This totally surrounds the dirt particle to form what you should know is a micelle. And now that you've formed a micelle, when you wash your hands with soap and water, they were dirty, the micelle looks polar to water, and the micelle says to water, or water says to micelle, I'm polar, you're polar, like dissolves like, let's go down the drain together. And they do. So you should know the structure of soap, nonpolar tail, polar head. Water's polar, dirt and grease are nonpolar. The key to this is like dissolves like. And when you mix dirt, water, and soap together, you form a micelle, and the micelle now looks polar to water, and water says to the micelle, you're polar, I'm polar, let's dissolve and go down the drain together. And they do. Now, if you remember, I said there are two types of lipids, saponifiable and non-saponifiable. And the non-saponifiable is the steroids. And I could spend a whole semester doing steroid chemistry and talking about them, which I'm not, but you should know how to draw the steroid ring skeleton. And that's this structure right here, six-membered ring. Next to it, fused, six-membered ring. Up here, a six-membered ring. The next door here, a five-membered ring. A, B, C, D. And all our hormones, all the steroids, have that skeleton, 6665. And you should know how to draw that. All right, let's go into carbohydrates. And a carbohydrate, you should know, is a polyhydroxyaldehyde or polyhydroxyketone, or a molecule that upon hydrolysis, excuse me, becomes a polyhydroxyaldehyde or polyhydroxyketone. By the way, poly is the Greek prefix for many, and that means there are a lot of OH groups in that molecule. Now, there's a Greek word called chirality or chiral. And chiral means handedness. And just like your hands, there's a right and a left. Certain molecules exist as chiral molecules and others are not. Now, when you put an A in front of a word, that means not. Achiral means a not chiral object. And you should know an achiral object and be able to identify it as something that has a non-superimposable mirror image. If you watched a video, I think it was the second semester or third I taught, or 170 at ECC, I spelled that wrong. It was super impossible. And then one of the students pointed out, and I said, oh, that's why students are having trouble. Bad joke, but true. All right. So a chiral object is an object with a superimposable mirror image. So my hands are a mirror image. They're not superimposable, so they're chiral. Now, in the videos, I asked you to, in the problem set, identify an object as either chiral or achiral. Hint, if an object in the name has the word right or left, it's always going to be chiral. Hint, if the object has the word right or left, it's always going to be chiral. So if I ask, is my right foot chiral or achiral? Immediately you should say chiral. If not, see if you draw the mirror image, is it superimposable? And you got to have some laughs to find out Dr. White never inherited any of the artistic skills both my mother and father had. My mother was a very good amateur artist. My father was a very good amateur carver. He did some beautiful work, so did my mother. All right, next we talk about chiral carbons. And chiral carbons are a carbon with four different groups or four different atoms or a combination of four groups or atoms. Oops, there we are. And if I were to ask you to circle the chiral carbons in the molecule, I were to ask, circle the chiral carbons. If a carbon has 2 or more hydrogens, it can't be chiral. It's out. So that means this is out. If a carbon is in a double bond, whether it's carbon-carbon or a carbon or a triple bond or carbon-oxygen, it's out. So these are out, can't be. Same thing here. That leaves us these 2 carbons. And if we look at these 2 carbons, hydrogen, hydroxy group, this is an R group, this whole thing would be R prime, 4 different groups. So you'd circle that. If we look at this carbon right here, we have a hydrogen, a bromine, this aldehyde, and this group, which one I call R prime. So there are 4 different things on that carbon. So this would also, you would circle. So if a carbon has 2 or more hydrogens, it can't be a chiral carbon. If a carbon is in a double bond with another carbon or oxygen, it can't be chiral. It has to have 4 different atoms or 4 different groups or a combination of 4 different atoms and groups, R groups. And that's a skill you should have. Now, next thing I talked about were enantiomers. And all that means is for my class, that's a molecule's non-superimposable mirror image. So if I were to ask you to draw an enantiomer, and we talked about Fisher projections, and a Fisher projection, every intersection of a line is a carbon. So there's also a carbon. But this shows stereochemistry. And how would you draw the enantiomer of this molecule? Well, this aldehyde is an achiral carbon. And this carbon here has 2 hydrogens, so it's achiral, so you don't have to worry about the mirror image. But this carbon right here, what's closest to the mirror, you'll see first in the mirror, and then what's farthest away, and that's how you draw the enantiomer. Now you can say, well, I can rotate that. Well, you can't, because that implies stereochemistry, and it's sort of like rotating a car this way or this way. They wouldn't be superimposable. Now, important chemistry when we talk about carbohydrates are the following 2: equilibrium. Notice I even printed here, no? This one, and I'll cover it, and this one. All right, let's look at this. Here we have the structure of glucose, and we have an alcohol at C5, and at the first carbon, an aldehyde. And from test 2, you learn that if you had a ketone or aldehyde, alcohol and acid, you form the hemiacetal or hemiketal. Now, when it's in the same molecule, you don't need the acid catalyst, and it's an equilibrium. And the red arrow shows you where you're going to form a bond. Remember, draw in this new bond because you're forming that. And this carbon here is this carbon here. And you should know both the forward and reverse reaction. If I give you the structure of glucose, And a double arrow, you should be able to form is hemiacetal, cyclic hemiacetal. If I give you this, you should be able to draw glucose. Same thing happens with fructose. Now, fructose, instead of being an aldehyde, at C2, you have a ketone. And again, the same equilibrium. And here, aldehyde or ketone plus alcohol and acid gives you a acetal, hemiacetal, or hemiketal. In this case, again, the hydroxyl group on C5 is this hydroxyl group and attacks the carbonyl carbon here to open it up to this carbon hydroxyl group. And it's don't forget to put in that bond. And so if you take fructose, which is the sweetest sugar, just look at a can of Coke or other things, they'll have high fructose corn syrup, in other words, fructose, and that's what making it sweet and taste good. And you should know this equilibrium. If I give you the structure of fructose, you should be able to draw the hemiketal of fructose. If I give you the hemiketal of fructose, you should be able to draw or write the name, same thing, draw or write the name glucose. Now, back when we had ketones and aldehydes, if you took two alcohols and reacted with an ketone or aldehyde, you got the acetal. Now, or ketal. Now, it turns out you can stop at the hemiacetal and react it with a different alcohol. And this is very important. Why? Because in the hemiacetal cyclic form of glucose, take another alcohol, replace the OH with OR double triple prime. And you should know this. This is the only new reaction. Now, a couple other things you should know. One, sucrose, also known as table sugar, it's the white stuff you put into your coffee, tea, or on your oatmeal or other things, or when you're cooking, is made up of fructose and glucose bond together. Starch is a polymer polyglucose. In both cases, they're held together by an acetal linkage. So if you have glucose, a lot of them, and acid, like an enzyme, you'll make starch. And again, it's an acetal linkage. Because of that, you take sucrose, and you should know this, acid and water, it breaks down back to fructose and glucose. If you have starch, you add acid and water, you do acid hydrolysis and acetal, and you get back to glucose. And that's why glucose is the most abundant sugar in our body, in our blood, because our body breaks down the starch to glucose. But if you eat sucrose, you'll also make some fructose. All right, listen carefully. Let me get subtle again. Subtle, aren't I, tonight? All right, leaving my class, besides knowing, and also for test number 4, how soap works and being able to describe it, you should know how to describe with words and a general reaction what happens when you eat in your stomach when you eat something with a fat or oil. Again, you should know how to describe with words and a general reaction what happens in your stomach. My stomach is here, and yours is over there, wherever. And that is in your stomach, there's acid and water. So there's acid hydrolysis of an ester. The key functional group in fats and oils is an ester. So in words, that's acid, hydrolysis, and ester. And you learn for test number 3, ester, H plus is acid, water. You get back the carboxylic acid and the alcohol you would have used to make that ester. And your body does that to fats and oils. You should also know when you eat a carbohydrate, how to describe that with words and a general reaction. Again, in your stomach, we have, I'm going to have some right now, real quick. Water, like I just drank. And one of the miracles of life in my mind is I have in my stomach, and you have cells that make hydrochloric acid, H plus. And carbohydrates are really polymers of an acetal. And here I have an acetal or ketal. You learned this for test 2, acid and water. Get back the aldehyde or ketone you would have used to make that acetal plus the alcohol. And you can see the micro mini 2. If you watched the videos, I talked about the twin sisters I had who got upset when I didn't balance equation. Oh, did they get upset? Right. But anyways, acid, eat a carbohydrate, acid hydrolysis and acetal. And here's the general reaction: acetal, acid or ketal, acid and water. Get back the aldehyde or ketone you would have used to make the acetal or ketal, plus the alcohol you would have used to make the acetal or ketal. So leaving my class, you should know how to describe how soap works. You should know how to describe with words and a general reaction what happens when you eat a fat or oil. That's acid hydrolysis of an ester. Here's the general reaction of acid hydrolysis of an ester. You learn for test number 3. I think I'm going to sneeze. Hold on. Excuse me. And you should know how to describe with words and a general reaction what happens when you eat a carbohydrate. In your stomach, there's acid and water. That's acid hydrolysis of an acetal. Because what holds glucose together in starch? Acetal linkage. So you have acid hydrolysis and acetal. For test 2, I taught you, here's the acetal or ketal, H plus acid and water. If you wanted to put HCl in here, you could too. I don't care. Either one works for me. Then you get back the aldehyde or ketone you would have used to make that acetal or ketal, plus the alcohol you would have used to make that acetal or ketal. Wow, that was a long night. And with that, I'm done. I'm going to stick around for a couple of minutes. Anybody has any last minute questions, I'll turn off the video, the recording, and I'll answer them. But I'm done. Remember, this Thursday, test number 4, I'll be giving online. Maybe even Wednesday night, I'll send out the password, make it available to you. You have until Friday, end of the day, 11:59 p.m. The upload is a single PDF file to D2L. Your test 4 answers. The following week, a week from this Thursday, will be the final exam. Friday, I'll put out an email, or even earlier, maybe even Thursday, giving you a breakdown of the final exam. And with that, I'm done. I can say "Gehen gesund," which is Yiddish for go in hell. And you know what I'm going to do now. Yep. Bye now. Bye. Bye. Stole that from Granny to Beverly Hillbillies. Bye.